Hey everyone, and welcome back to the Deep Dive.
Great to be here.
Today we're plunging into a topic that's generating incredible buzz and, as we'll uncover, some surprising challenges. We're talking about using large language models, or LLMs, to simulate human behavior in social science research.
Yeah.
Imagine being able to predict how people might respond to, say, a survey or an intervention without running those expensive, time-consuming studies with actual humans.
It sounds like science fiction almost.
Right, but it's becoming a reality.
It really is. Researchers are calling these simulated data sets silicon samples, and the potential, well, it's immense.
Huge potential.
Accelerating our understanding of human decision-making, rapidly testing hypotheses. The allure is undeniable.
Definitely.
But as the research we're exploring today from Jamie Cummins highlights, there's a significant, often overlooked challenge lurking just beneath the surface.
Exactly. So our mission today is to unpack this emerging field, understand its incredible promise, and then really dig into what Cummins calls analytic flexibility.
That's the key phrase.
Because, you see, the way these silicon samples are created involves a multitude of choices.
Well, a lot of choice.
And as our deep dive reveals, even small adjustments can lead to vastly different outcomes. It's like navigating a garden of forking paths.
A very fitting metaphor.
And we want to make sure we don't accidentally wander off the trail.
Right.
So, okay, let's start with the upside. What makes researchers so excited about using LLMs as simulated participants? What's the big draw here?
Well, the core idea is that LLMs, which are trained on, enormous amounts of human-generated text, might just approximate the underlying processes that drive human responses.
Okay.
If we can truly capture that, the impact on social sciences would be transformative.
I can absolutely see why. Think about the sheer efficiency. For one, researchers could maybe predict responses from vulnerable or hard-to-read populations without needing those intensive, expensive, real-world studies.
Which are often really difficult to conduct.
Exactly. And as Sarstedt and colleagues pointed out recently, this could significantly improve how representative and diverse our research actually is.
And it goes even further. Imagine prototyping and refining studies iteratively with LLMs before you ever deploy them with humans.
Like a dry run.
Precisely. Antis and co-authors discussed this, suggesting it could make research much more robust right from the get-go.
Makes sense.
Plus, Zabaleta and Lehman highlighted how quickly you could compare multiple competing hypotheses.
Which is a huge bottleneck in research sometimes.
Definitely. It's a potential game changer for academic inquiry.
So we're talking about models that can not only predict what people might do, but potentially how strongly they'll react. Almost like a human forecaster, but, on demand.
That's the idea, and early applications have shown some remarkable promise. May and his team, for instance, found that models like ChatGPT 3.5 Turbo and GPT-4 could reproduce human-like behavior in 6 classic economic games.
Like the prisoner's dilemma? Those kinds of things?
Yeah, exactly. Those famous scenarios researchers use to study decision-making. The LLMs often align pretty well with average human choices.
That's pretty wild. So the AI can play these games and behave sort of like a human would.
Seems like it in some cases. Other researchers like Park and colleagues even saw LLMs replicate results from the ManyLabs 2 project.
Oh yeah, that was that huge replication effort.
Yeah, a massive collaborative project to see if key psychological findings hold up. The LLMs managed to replicate some results.
Okay.
Though they did note a caveat. The LLM sample showed less response diversity than real humans.
Interesting. Less variety in the AI responses. That seems important.
It is. But on the other hand, Dillian and co-authors found a very strong correspondence, like really high correlations between LLMs and humans on moral judgment tasks.
Correlations over 0.90, I saw.
Exactly. And also in areas like voting behavior and problem solving, some studies went even further.
How so?
They actually provided demographic information to the models, things like age, gender, income.
Oh.
Hewitt and his team found GPT-4 could simulate social science experiments with these specific demographic profiles. And its estimates of treatment effects correlated strongly with actual outcomes.
What's the correlation there?
An impressive R value of 0.85. They even suggested it performed about as well as human forecasters.
That's quite something. So you tell the model, act like a 40-year-old woman from California, and it gets pretty close.
Well, that's the ambition anyway. Argyle and others in 2023 showed that by systematically varying these socio-demographic variables in the prompts, models like GPT-3 and GPT-4 could produce outputs that approximated human survey data distributions across different psychological and political domains.
Wow.
This really points to the big goal here: creating detailed, representative virtual populations, digital stand-ins for real people.
Okay, that all sounds incredibly hopeful. Almost maybe too good to be true.
Mm-hmm.
You mentioned a threat earlier, a significant challenge. Where do the cracks start to appear in this promising picture?
Well, the positive findings we just discussed, they represent a relatively small number of successful examples, really.
Yeah.
Other work looking into silicon samples hasn't been quite so straightforward. It's revealed some important limitations.
Okay, this is where it gets really interesting. Give us an example of where things started to look a bit shaky.
Sure. Take Schroeder and his team's work on moral judgments. They found that if scenarios were reworded slightly, keeping the surface meaning similar, but subtly shifting the semantic emphasis.
The nuance.
Right, the nuance. Human participants would adjust their evaluations based on that nuance. LLMs, however, often ignored these subtle differences and produced nearly identical ratings. This suggests, a fundamental disconnect in how models understand meaning compared to humans.
So the models were missing those delicate shades of meaning that we humans pick up on. I can see how that could be a huge problem.
Absolutely. And then Lutz and colleagues showed something perhaps even more surprising.
What was that?
That even minor variations in prompt formatting could dramatically affect outcomes.
Formatting.
Yeah.
Like bold text or bullet points.
Exactly. Even when they used careful prompt design and demographic alignment. This sensitivity to seemingly irrelevant prompt features things you wouldn't think should matter has been reported in other cases too.
That's unexpected. I mean, you'd think such a powerful model would be robust to minor formatting tweaks.
Mm-hmm.
What does that tell us?
It tells us the models aren't always robust in ways we might intuitively expect. They can be brittle.
Okay.
And even studies with positive conclusions often came with caveats. Hewitt and his team, for instance, noted that LLM predictions tended to overestimate effects and needed adjustment.
Right.
Park and colleagues, as we mentioned, found less response diversity.
Less variety.
Yeah. And sometimes results just flat out contradicted each other, like Wang and his team finding LLMs generally simulated response distributions accurately, which, clashed with Park and colleagues' findings.
So inconsistencies across studies, too.
Exactly. And these inconsistencies point to a deeper, more systemic problem.
Okay, let's unpack this deeper problem. This is what the paper calls analytic flexibility, or the garden of forking paths. Can you explain what that means in this context?
Sure. The garden of forking paths isn't a new idea. It's a well-known concept in social science.
Right.
It basically describes how researchers make many, many choices during a study, from how they collect data to how they analyze it. And these choices, even if they seem reasonable at the time, can significantly impact the results.
And historically, this flexibility has sometimes led to issues, right? Like inflated false positive rates, problems replicating findings.
Exactly, in standard human subjects research.
And the paper argues that LLM research is even more susceptible to this problem.
Precisely. When you're simulating human responses with LLMs, researchers face an even wider range of analytic decisions. And these decisions can have a major, often poorly understood, impact on the output. It's like having 1,000 more forks in the path than usual.
Wow. Okay, give me some examples. What kind of choices are we talking about?
Oh, there are loads. First, there's the model choice. Which specific LLM are you using? Is it ChatGPT, Llama, DeepSeek? Is it a chat assistant version or a more specialized reasoning model? Open source versus proprietary? Fine-tune or general purpose?
So many options just there.
And different models can give you dramatically different results.
Let's see. So it's not just which AI, but what kind of AI within that family.
Precisely. Then you have model hyperparameters.
Hyperparameters.
Yeah. Beyond just the words in the prompt, there are these background settings. Things like temperature.
Temperature, like how hot the computer gets.
No, not quite. It's more like a creativity dial. A low temperature makes the model's responses very predictable, very focused. A high temperature encourages more variety, sometimes more randomness, maybe even quirkiness.
Oh, okay. Like a risk setting.
Sort of.
Yeah.
Then there are other settings like reasoning effort for some advanced models, or top K and top constraints, which also shape the kind of output you get.
Wow, that sounds like 1,000 tiny dials you could be tweaking, almost like trying to mix a perfect song without really knowing what half the buttons do.
It can feel that complex, yeah. Then next, think about demographic information. How much, if any, do you provide to the model?
Right. Do you tell it age, gender, income, political views?
Or nothing at all? This choice can significantly influence its output.
Makes sense.
Also, consider the scale prompting strategy. If the LLM is completing a series of survey questions, like on a scale,
Like a personality test or something.
yeah, should all the items be presented in one single giant prompt, or maybe scale by scale, or perhaps even item by item, one question at a time?
So not just what you ask, but how you structure the actual request to the AI.
Exactly. And then there's the information and context you provide. Are you just giving the bare survey items, or are you also including definitions of the psychological constructs being measured? Or maybe even typical human response patterns like psychometric norms.
This is giving it hints.
Potentially. And finally, output handling. Are you simply using the raw scores the LLM spits out? Or are you post-processing them, maybe rescaling them based on known population distributions?
So many steps I have to get the answer to.
Each of these choices creates a new path in that garden, a different potential outcome.
That's a huge list of choices, each one potentially leading to a completely different result. It's a little unsettling, actually.
It is, and this is precisely what Cummins set out to investigate empirically. The study aimed to directly measure how variations in just a relatively small number of these analytic decisions could affect how consistent these silicon samples were compared to real human data.
Okay, so how did they go about it? What was the setup?
The researcher used an existing dataset, the Attitudes, Identity, and Individual Differences dataset, or AID. It had data from 85 real human participants.
Okay.
These humans had completed two specific psychological scales. First, the belief in a just world scale, the BJW scale. That measures the belief that people generally get what they deserve in life. And second, the gut feeling scale, which assesses implicit preferences, in this case towards African Americans versus European Americans.
Okay, two different measures, and then they systematically varied the LLM settings for these two scales.
Exactly. They focused on 4 key analytic decision points that we just discussed, basically, and they mixed and matched them. This led to a total of 252 possible combinations for generating silicon samples for those 85 virtual participants.
252 different ways of asking the AI. That's a massive undertaking.
It really was. So the 4 things they varied were: 1, model used. They tested a whole range of popular LLMs, different ChatGPT versions like 5 Mini, 4.0, 3.5 Turbo, but also others like Llama and DeepSeek.
A good mix.
Yeah. 2, temperature reasoning effort. They explored different reasoning effort levels for some models and a range of temperature settings from 0, which is very deterministic, up to 1.5, which is pretty random.
Playing with that creativity dial.
3, demographic information provided. They tried 3 levels: no demographic info at all, just age and gender, or really extensive demographic info, including country, education, ethnicity, income, political identity.
Got it.
And R4, scale sampling strategy. They compared presenting the survey items all in one, scale by scale, or item by item.
Okay. With all those choices resulting in 252 different silicon samples, what were they actually looking for? How did they judge if a silicon sample was good or not?
Right, good question. They evaluated the LLM's consistency with the real human data based on 3 crucial data features.
Okay.
First, ranking participants. How well did the LLM predicted scores for each virtual participant correlate with their actual human scores? A higher correlation closer to 1 means the LLM was better at predicting individual differences, who scored high versus low.
Right, getting the order right.
Second, estimating response distributions. How closely did the overall spread and shape of responses from the silicon sample match the distribution of the real human responses? They used a metric called Wasserstein distance.
Wasserstein distance.
Yeah, it essentially measures how much you'd have to shift the LLM's answers around, like moving piles of sand, to make them look exactly like the human answers. A smaller distance means a much better fit, a closer match in the overall pattern.
Okay, so how will it match the crowd?
Pretty much. And third, estimating the relationship between scales. How well did the correlation between the BJW scale and the gut feeling scale and the silicon sample match the actual correlation found in the human data?
So did the LLM correctly capture how those two different concepts related to each other in people?
Exactly. Does it understand the psychological structure?
And finally, I think you mentioned they looked at consistency across these features. Like, if a setup was good at one thing, was it good at the others?
Yes, that was the last piece. Consistency.
All right, so after all that meticulous analysis, crunching the numbers on 252 different scenarios, What did this extensive study reveal? How consistent were these silicon samples with real human data?
Well, the results were pretty stark. They vividly highlighted the severity of this analytic flexibility problem.
Oh,
For ranking participants, the correlations between the silicon samples and the human data were, frankly, quite poor, often barely better than random chance.
really?
Yeah, we're talking numbers ranging from negative 0.27 up to positive 0.36 for the BJW scale, and negative 0.25 to positive 0.32 for the gut feeling scale.
So close to zero correlation much of the time.
A lot of the time, yes. Now, correlations were generally slightly better when extensive demographics were provided,
Okay, that makes some sense.
but they still remained relatively small overall. This means the models really struggled to predict how any individual person would score, even when given detailed demographic information about them.
So even with all that input,
Mm.
it wasn't really much good at predicting individual responses accurately, not consistently anyway.
That's right. Then, for response distributions matching the overall crowd pattern.
How did they do there?
The LLM-generated distributions were measurably different. The Wasserstein distances were significantly larger than the distances you typically see just comparing two random halves of the human sample.
So more different than humans are from each other.
Yes. For example, for the BJW scale, typical human-to-human distances averaged about 0.03, while the LLM-to-human distances averaged around 0.19.
That's a pretty big gap.
It is. It means the LLMs often fail to accurately model the overall spread and shape of human responses. The silicon samples just weren't reflecting how humans collectively respond.
Okay. And what about the relationship between the two scales? The correlation?
This is perhaps where the forking paths became most obvious, most dramatic.
How so?
Okay, so the actual correlation in the human data between the belief in a just world scale and the gut feeling scale was 0.26, a modest positive correlation.
Okay, 0.26. Got it.
But the LLM estimated correlations across those 252 different setups varied wildly. They ranged from negative 0.26 all the way up to positive 171.
Wow, that's a massive range. So depending on which settings the researcher chose, they could conclude there was a moderate negative relationship, no relationship, a weak positive one, or a very strong positive one.
Exactly. That's the problem. You could get almost any answer depending on seemingly arbitrary choices.
And it's far from the true value of 0.26 in many cases.
Very far. And here's a critical detail that really drives it home. Even the most accurate LLM prediction.
The one closest to 0.26.
Yeah, that one had an R value of 0.24, incredibly close to the human 0.26, but it was achieved with a very specific, unique configuration.
Which one?
It was ChatGPT 3.5 with the temperature set to 1, using the extensive demographic information and presenting the items one by one.
Okay.
But just changing the temperature slightly from 1 to 1.5 made that same model massively underestimate the correlation it dropped to negative 0.18.
Whoa.
And decreasing the temperature slightly to 0.5 made the correlation estimate basically 0.00. Small, seemingly minor changes had these huge, unpredictable effects on the outcome.
So definitely no single best path emerged.
Yeah.
But was there any consistency across the different evaluation metrics? Like if a model setup was good at ranking participants, was it also good at estimating distributions or the relationship between scales?
Unfortunately, the answer there was generally no.
Really?
Yeah. The correlations between how well a configuration performed on one data feature versus another were mostly small. So a silicon sample might, by chance, do okay at ranking participants, but be terrible at approximating response distributions, or vice versa.
So you couldn't even rely on one metric to predict another?
Not really. There was no one-size-fits-all configuration that optimized accuracy across all dimensions. And get this, for distributional approximation, there wasn't even a significant correlation between the two scales. Meaning a configuration that happened to be good at modeling the distribution for the belief in a just world scale wasn't necessarily good at modeling the distribution for the gut feeling scale, even within the same simulation run.
Wow. That really drives home the inconsistency. So what does this all mean for researchers who are trying to leverage LLMs? If these small, seemingly defensible choices can lead to such dramatic and inconsistent results, it feels like we're on incredibly shaky ground.
It raises a really important question, doesn't it? If there's no reliably best configuration, how can researchers possibly trust these silicon samples to inform critical decisions? The implications are quite stark.
Like what?
Well, for one, it could lead to inefficient research design. Imagine researchers using silicon samples to plan studies or estimate effect sizes. They could be led to very different conclusions based purely on these arbitrary analytic decisions they made when setting up the simulation.
So they might design a study that's too small to find a real effect, or way too big and wasteful.
Exactly. They could end up underpowering or overpowering their studies, wasting time and resources, and completely defeating the whole purpose of using LLMs for efficiency in the first place.
And beyond just efficiency, what about the impact on the actual research outcomes or interventions?
That's where it gets even more concerning, potentially. If LLM predictions are used to guide decisions about, say, which interventions to deploy in human samples.
Like which therapy approach to try or which public health message to use?
Right. If the LLM results are inconsistent or just plain wrong, depending on the setup, you could end up choosing ineffective or maybe even harmful approaches based on faulty silicon evidence.
That's a serious risk. And the paper highlights a particularly worrying concern related to vulnerable populations, doesn't it?
It does, and this is really important. The argument is, if we can't even find a reliable configuration for accurately simulating data from typical research subjects, the university students who are likely well represented in the LLM training data,
Right.
then it's even less probable that these models will provide accurate insights into non-weird populations.
Weird meaning Western, educated, industrialized, rich, and democratic.
Exactly. Those groups often underrepresented in research, or other vulnerable or hard-to-reach populations.
So what's the risk there?
The risk is significant, creating an illusion of representation. You think you're getting insights into these groups, but you're actually just getting plausible-sounding noise generated by the model. You end up, as Wang and colleagues warned, speaking over these very populations.
Hindering their inclusion rather than genuinely facilitating it.
Precisely.
That's a profound ethical concern. To mistakenly believe you're gaining insight when the model is just, making stuff up based on potentially biased training data.
Absolutely. And given these challenges, the study calls for really urgent attention here. The paper uses strong language, saying the social sciences might be sleepwalking into a literature filled with results that are strongly influenced by arbitrary methodological decisions.
Leading to findings that aren't robust, that can't be replicated.
Yeah, reminiscent of past crises around analytic flexibility and replicability in other fields. We've seen this movie before, in a way.
But the flip side is, this also means we have a rare opportunity now, while this is still relatively new, to get ahead of the problem.
Yeah.
What can researchers actually do to move towards better, more disciplined practice?
Well, the very first step is simply awareness. Just recognizing that this garden of forking paths exists and is maybe even more complex with LLMs.
Acknowledging the problem.
Right. Researchers need to carefully map out and consider all the analytic choices that might affect the output, rather than just relying on their intuition about what should matter based on human responses. LLM behavior can be influenced by very unintuitive things like formatting.
So don't just blindly ask the LLM. Understand how you're asking it and what all those underlying parameters actually mean and how they might interact.
Exactly. And crucially, acknowledge that LLMs probably can't be used straight out of the box to create valid and robust silicon samples. It takes work.
Okay. Are there specific tools or methods recommended?
Yes. The paper advocates for concrete tools. One is specification curve analysis.
Specification curve.
Yeah, it's a visualization tool developed by Simonson and his team a few years back. It basically maps out a whole range of plausible analytic configurations, like many of those 252 paths, and shows you the full distribution of results you get.
So you can see the variation.
Precisely. It helps researchers see the heterogeneity, see which dimensions like model choice versus temperature versus demographics seem to have the most significant sway on their results. That guides them on where to focus their scrutiny and testing.
So it helps you see which choices really matter the most for your specific question, letting you know where to concentrate your validation efforts. That sounds really smart.
It's a powerful technique. The other key tool recommended is study registration or pre-registration.
Like we see in clinical trials in other fields.
Exactly. Registering your analytic choices in advance helps combat undisclosed flexibility or packing the simulation settings.
How would that work for silicon sampling?
Well, it could mean clearly defining upfront the difference between initial piloting or exploration of configurations and the final canonical configuration you plan to use for making actual decisions or drawing conclusions. It also allows for transparent documentation of which configurations were tried and maybe rejected, which is invaluable information for the field and helps prevent others from repeating dead ends. It combats confirmation bias.
So it's not just about documenting the final choices, but actively interrogating them and being transparent about the entire process, including the paths not taken.
Yes, absolutely. And the goal here isn't necessarily to find one single best strategy that works for all contexts, because the study pretty clearly showed that it probably doesn't exist, even within their constrained demonstration.
Right.
Instead, the aim should be to identify classes of strategies or configurations that perform reliably well in particular types of situations or for specific research goals.
Tailoring the approach.
Exactly. But that requires dedication, careful attention, lots of piloting, and iteration for each specific research context. It's real scientific work.
This deep dive has certainly eliminated the dual nature of silicon samples. On one hand, they offer this incredibly exciting frontier for social science, promising efficiency, accuracy, broader representation.
Huge potential.
But on the other hand, as Jamie Cummins' work powerfully demonstrates, they come with significant risks if they're not approached with really careful consideration and methodological rigor.
That's right. The promise of revolutionizing human subjects research really hinges on our ability as a field to navigate this analytic flexibility responsibly. Without learning from past mistakes in other areas and without actively interrogating our methodological choices with these new tools, we risk building a whole literature that's just fragile, misleading, and ultimately unproductive.
The good news, though, is that we have this opportunity now, right at the beginning stages of this technology becoming widespread, to try and set robust standards.
We do.
It means asking tough questions about our models, our prompts, our parameters, our data processing. It means embracing tools like specification curves and pre-registration to truly understand the landscape of choices we're making.
And fundamentally, it means recognizing that creating valid and robust silicon samples is not some easy, out-of-the-box solution. It's a thoughtful, iterative process that demands real scientific discipline.
Yeah.
The future of social science, at least in part, depends on how well we choose our paths in this new, complex garden of forking paths.
So, as you, our listeners, reflect on this, maybe consider, when does the pursuit of efficiency with powerful new AI tools cross the line? When does it go from genuinely advancing knowledge to simply creating an illusion of understanding?
That's the critical question.
It's definitely a question worth pondering as we continue to explore the ever-evolving landscape of AI in our world.